all across the nation. So I think we will be good to go in just a minute. So we've got it all going. Thank you, everyone.
Do you want to put up the cool slide, Pavel?
I had it up.
Yeah, it's there in another channel.
Hold on. Yeah, I had it. Yes, Zach, let me put it up so that you can take the picture you want.
How many miles have you walked, Zach?
Well, I have 19,935 steps.
Oh,
So
wow.
whatever that translates to, I think that's probably 6 or 7 miles, something like that.
All right. Well, I think we're just about ready to start. Zach, you want to take your screenshot now?
I have got it.
Awesome. In that case, I can stop my sharing and welcome everyone back to the 4th session of FPTalks 2020. And kicking off this session is going to be Theo. So Theo, please go right ahead.
All right, I'll hit that recording button.
Excellent.
And
then share the screen.
Share. All right, can everybody see the slide? All right.
Yep.
I presume that is yes. All right. So the next 10 minutes, I'm going to talk about the Universal Library. It's an effort to build a collection of number systems that will allow us to do some research in multi-precision algorithmic research. So we are looking for number systems and tailor them to the application. That's really the goal. So what is, how do I move forward? There we go. There we go. The Universal Library is a C++ header only, featuring plugin replacement for native arithmetic types. Right now, we have a broad range of number systems, and they're all sort of tailored to study efficiency improvements for more complex algorithms. We have integers, decimals, fixed points, rationals. Then we, of course, have the linear and tapered floating points and logarithmics. And this day, I've learned of a handful more. So it would be quite nice to add these when we get time or when people are interested in contributing. As I said, the whole purpose for the library was to start building a collective knowledge base for tailoring number systems to applications. And in that process, we sort of discovered that when you don't know an application, you really would like to have a number system that is multi-precision and adaptive. So we have some adaptive multi-precision pieces that we then use for characterization. But then the next step is when you know your characteristics of your algorithm, you can then go into a configuration, an arbitrary configuration, fixed point or floating point or posit, and make progress on potentially a hardware study or a power estimate. Why, taking a step back, why are we sort of interested in this? Well, one of the observations that you have in the universe of embedded intelligence is that we see this rapid proliferation of hardware environments. And another sort of important aspect of this is the hardware environments tend to be very concurrent. So the development of new algorithms and to deliver intelligence to these embedded devices, it would be nice if these algorithms represent or produce the same results across all these different form factors and concurrency mechanisms. And that's one of the reasons that we got interested in building this tool set so that we can, one, get information about the difficulties there, and then hopefully research and develop some answers to these to overcome these problems. So the vision of Stillwater is really to build that high productivity runtime for these embedded intelligence applications, and then the Stillwater company will optimize the performance for these underlying platforms so that customers can basically use that platform and move to whatever their SKUs demand without penalty. So if you then look at the characteristics of these embedded intelligence, it's the number systems that really drive innovation there. So the first observation is pretty obvious, is that most constraint solvers are memory bound. So any efficiency improvement in information encodings will have commercial value. This is clearly borne out by all of the big incumbents that are active in the AI deep learning space. All of them have ditched IEEE floating point, and they've replaced it with something that is much more energy efficient, much more resource efficient, so that they can build services that are 100x faster, 100x more capable than their competitors. But in deep learning is not the only application. There is still model predictive control, any type of simulation mechanisms. So there's still many improvements that that can be pursued. These pertain everything from discretizations and curve fittings to transformations and adaptions. The one that I'll focus on a little bit today is the numerical stability within different concurrency environments, and that's where the posit angle comes in for those that are keeping score. So we are part of the steering committee for the posit architecture, and the reason that we started looking at it was this this problem of reproducibility when you have a parallel processor that is thousands of cores. The fact that that posits sort of articulate a solution to user-defined rounding or having an answer to rounding error, that was what got us involved with the posit arithmetic standard, and we started Universal actually as a posit hardware verification library. But once we sort of got more in the marketplace and asked people what their pain points were, they were all asking for a much broader range of number systems. So that's when we started with integers and fixed points and rationals. So just so that this presentation can also be seen independently of the other talks, just a quick introduction to posits. Posits are a tapered floating point system that is parameterized in two variables. One is the size of the posit, and the other one is the size and the number of exponent bits. That parameter defines a scaling factor, and that is what tapers the encoding of the reals, what gives posits this really rich dynamic range for small sizes. The other aspect of the posit standard is the superaccumulator. So the quire is an entity that allows you to accumulate unrounded results, and these results can come from additions and multiplies, and now give you an opportunity to do a non-trivial computation without incurring any rounding. The only rounding that happens is when you, as a programmer, make an assignment back into the posit that you set. And the example that is given here is a typical fuse dot product that is implemented in the Universal Library. And you can see that sort of the quire is programmable visible. It is tied to the posit that it's accumulating. And the reason for that is that the size of that quire is very dependent on the dynamic range of that posit. So they're sort of tight, and then they become available to the programmer to direct that computation that they would like to have more fine-grained control over the rounding error. And then the last piece in the context of developing algorithms and characterizations of perfectly tailored number systems for algorithms, the valid encoding takes some of the old unum characteristics, which is the U bit, and adds to that an upper range and a lower range interval type arithmetic to it. And the valid encoding is really useful for doing these characterization type studies where you're trying to discover what the numerical properties are of the execution that you're observing. As said, the Universal Library is an open source library. You can pick it up here at github.com/Stillwater SC Universal. We have roughly about a dozen contributors, and we are always looking for folks that are willing to either implement their number system of choice or are interested in contributing examples of numerical properties or numerical problems that need to be solved by a tailored number system. We started Universal about 3 years ago, 2017. It has been integrated in production quality code in about the past 2 years. It has platform support for anything from Linux to Arduino, and pretty much supports all the compilers that we can get our hands on. On the left-hand side, I give you a quick overview of how the library is organized. The two major segments, of course, to call out are the areas where the number systems are managed. You can see that in the sort of the middle of your screen. And there you have your decimals, your fixed points, your floating points, your integers, and your logarithmic entities. And then there is an example section where we basically take computational science and computational engineering applications, boil them down to sort of the essence of either the algorithm that is the bottleneck or the algorithm that is the performance, power, or accuracy problem. And we are boiling them down there and present them as examples where people can play with it and get examples and ideas of what can be done next. And it's sort of important, sort of the basic tenet of the Universal Library is to create the separation between the driver in which you set up the selection of your number system and the kernel that will be parameterized in the numbers that the number systems that you would like to select. So here's a very simple example. There's a driver that selects a posit and then articulates a real number system that has that property, that has the posit's properties, will create variables and then calls these kernels that are parameterized in these number systems. So another more complicated example would be a conjugate gradient, where you have a residual calculation that would need high precision, and you would have a linear algebra sparse matrix vector operator that could be done in lower precision. So there, the parameterization would happen in 2 parameters. And that's the basic essence of how we sort of build Universal. There's a driver that sets up your number system selection, and then there is a parameterized kernel that can take these different number systems and produce the arithmetic that you're interested in. Of the past year, as indicated, we, Stillwater, are mostly interested on building now on top of that, particularly taking advantage of the Quire and creating these, what we call high-performance reproducible libraries. And the past year, we've built a runtime that is a matrix tensor library. That actually hides all this nuance between selecting a linear algebra operator that has a fused dot product operator. So for example, if you give it a Krylov solver, if you give a Krylov solver in this MTL a posit value, it will actually use fused dot products in the Krylov solver. And if you give it an IEEE, it will use dot product operator. And then on top of that, we are basically building these hyper libraries specifically for the application spaces that they're specialized for. So we have a BLAS, we have a DSP, we're working on a control and a deep learning mechanism. And then the last piece that is sort of going to see some activity the second half of this year is tensor compositions. Then to summarize and to sort of give you an example of the type of things that we've been doing, run simple empirical studies where we're basically looking at the trajectory that the ODE solver goes through as you give it different posits, right? And there you can see that sort of the 16-bit, 18-bit posit would be a place where if you would build a piece of custom hardware, you would like to put some more energy on trying to understand what really the cutoff is, where you would lose accuracy or build the wrong predictions. So in summary, we are finding ourselves in this really rapidly changing environment where systems are getting computes embedded in them to imbue these systems with intelligence. These products really need performance and flexibility. And because these are spread out over skews that have very variable degrees of concurrency. Reproducibility in that context of multiple skews of concurrency is very important for the productivity of building these algorithms. And the Universal Library is sort of presented here as the means with which you can accelerate your own algorithmic research so that you can maximize performance or power efficiency for the algorithms that you may be interested in. So with that, any questions?
Excellent. So thank you, Theo. So we'll be taking questions live on Zoom as usual using the raise hand button, which you can find in the participants sidebar. But I'll start with a question off of the Slack. Zach, do you want to go ahead and ask your question?
Yeah, sure. So I was just curious. I remember that in the past there were some challenges maintaining universal due to the parameterization in terms of C++ templates. And I was wondering if in hindsight, like that ended up being a big win, or you'd do it differently if you could start over.
Well, the parameterization really was a problem when you try to export it or support C environments like Golang or Python or R, right? That's where the C++ parameterization offers thousands of number systems, and you just can't manually build the shims to support C-like languages. So that's the biggest problem. Second problem that we really ran into is we started it off as a hardware verification library. So we erred on the side of flexibility, and that gave us some grief on the performance side, right? So we're fixing that now with these different storage classes that have much higher performance. But to summarize the answer to your question, did the C++ parameterization cause grief, and would you do it differently now? The answer is no, because when you look at the other number systems that have come after posits, they have all been actually adding more parameterization to them. That is not the difficulty. The difficulty is really supporting the Python environments of the world, right? That is where C++ is just so much template. C++ is just so much more flexible that it's tricky to then provide that flexibility to a Python, NumPy, or SciPy environment.
So I see that there's many more questions on Slack, but I'm gonna try to move along to the next talk. That's gonna be Wonyeol. So Theo, I'm gonna stop your screen sharing. And
I think you muted yourself, Pavel.
oh goodness, I'm sorry. Yes, thank you, James. I was muted. So thank you, Theo. Wonyeol, if you could start recording and then start your talk.
Sure. Let me see.
You're recording, and we can see your
Yes,
slides.
I'm recording. And could you see my slides? Okay. Okay. Thank you for the introduction, Pavel. So I'm Wonyeol. I'm a graduate student at Stanford, but currently taking a leave to do some kind of alternative military service in Korea. So anyhow, I'm going to talk about some verification problem for the math.h implementation. So this is a joint work with Rahul and Alex. And this talk is based on the two papers presented at PLDI and POPL. Okay, so let's get started. Okay, so to describe the problem that we want to solve, let's consider the log function and its floating point implementation as shown in the slide. And this is a floating point implementation because it uses floating point operations such as subtraction and multiplication colored by blue. But as you know that floating point numbers have a fixed number of bits always, but the log value, the exact mathematically exact value of log usually have infinite number of bits. So this indicates that any floating point implementation cannot compute the mathematically exact result for most inputs. In other words, there must be some kind of a precision loss for any floating point implementations. And you're particularly interested in finding a tight bound on the precision loss of those floating point implementations. So this is a problem that we are interested in. And formally speaking, suppose that you're given a mathematical specification F and its floating point implementation P, and also we're given an input interval X. Then our goal is to find a small quantity theta automatically that bounds some kind of error between F and P for all inputs in the capital X. So in other words, you'd like to prove a bound and the maximum precision loss of the floating point implementation. Okay, this is a problem that we want to solve. And at least the problem statement looks quite simple, right? But as we solved this problem, we found that solving this problem is not that easy. And in this talk, I will mainly focus on the challenges, the two main challenges that we encountered when we solved this problem. And the first challenge that we encountered is that those kind of floating point implementations, especially industry standard implementations of math.h, such as Intel's implementation, usually use floating point operations as well as bit level operations and intermix those two types of operations. So what I mean by bit level operations are those operations that directly manipulate the value of each or some parts of bits, such as bit shift operation like PSLLQ in the slide, or bit shuffle operation like PShuffD in the code. Then some of you might wonder that how can you actually use those kind of bit level operations in a meaningful way in floating point computation. And to explain that, let's recall the definition of floating point numbers. I think most of you are familiar with the definition. And the important point is that the parts of the 64-bit of a floating point number is partitioned into three regions. And each part always represents some numbers to a part of the floating point representation, like most significant 12 bits are assigned to sign and exponent bits and so on. And by using this fact, you can actually use those bit level operations in floating point computation. And this is a favorite example to show, my favorite example to showing that kind of intermixes. So suppose that we are given an integer n and like to compute 2 to the n in double precision number. Then a naive way to solve this problem is to do a bit shift to 1 by n to obtain 2 to the n in integer, and do the conversion operation to get the double precision number 2 to the n. However, this approach has two main problems. First one is that the conversion operation is computationally expensive. And more importantly, this approach works only for a small range of inputs. And actually, there is a more efficient and scalable way to solve this problem. And that approach is the following. So consider the integer n, and then do the integer addition by 1023, and then do the bit shift operation by 52 bits. Then the resulting bits are magically equal to our desired output. And this approach actually is more efficient than the left approach, and also it works for a wider range of inputs. And as we analyze the floating point implementations of math.h library, we figured out that such bit level operations are ubiquitous in those implementations. But you can see that reasoning about such mixed codes is not that easy. And this is mainly because the behavior of floating point operations are kind of continuous, but those of bit level operations are kind of discrete. So those two conflicting nature makes the reasoning of those mixed codes difficult. So that brings the first challenge that I mentioned earlier. And we partially solved this issue and presented our results at PLDI. And because of time limit, I'm not going to talk about our approach in more detail. And I'd like to move on to the next challenge, which is that the floating point, those kind of floating point implementations are usually claimed to have very low precision loss, namely less than 1 op error. So to explain what those 1 op error bound means, let's assume that the log implementation has that much precision loss. Then it means that for any input x, the floating point output of the implementation must be one of the two closest floating point numbers to the mathematically exact result. And as you can see, this error bound is quite tight, and this claims a very strong accuracy of strong bound on the accuracy of the floating point implementation. Okay, so we now understand that 1 op error bound is a very strong claim, but then why is it difficult to prove that 1 op error bound? And to explain that, let's look at some of the results from our first paper. So this shows the op error bound that we obtained for Intel's log implementation. And you can see that our error bounds are above the 1 op error bound, 1 op error that we want to prove. But not only that, we also see that for some input ranges, the op error bound is very large, like 10 to 14. But we would like to, our goal is to prove the 1 op error bound. So there is a big discrepancy between our goal and what we proved. And some might wonder why we obtain such loose error bounds. And the main culprit of that loose error bounds is that floating point operations are in fact exact in some cases, which might quite surprise to some of you because floating point operations are usually introducing rounding errors. And those exactness happens in some special cases, like if you multiply some floating point number a by 2 to the n, where n is integer, then that operation, that floating point operation, is always exact if the mathematically exact result is not very small. And also, the similar result holds for subtraction. So if two numbers are close to each other by a factor of 2, then the floating point subtraction is actually mathematically exact to the mathematically exact result. So it does not introduce any rounding errors. And the floating point experts who implements the floating point library use this kind of exactness result to get a high accuracy implementations. But standard error analysis usually ignores such exactness results, thereby sometimes constructing imprecise abstractions of floating point computation. And this is the main reason that why we obtained such loose error bounds for some cases. So this brings the second challenge that I mentioned earlier. And we also partially solved this problem and presented it at POPL 2 years ago. And so I'm not going to talk about our approach to solve this problem, but I will just show some of the main results from the paper. So here, the y-axis represents the op error bound that we found, and the x-axis is input values. And those two graphs are for Intel sine and log implementations. And the blue lines show our error bounds. And you can see that our bounds are well below the one-off error bound, one-off error that we wanted to prove. Not only that, you can see that the red dots represent the actual off errors. And you can see that our error bounds are quite tight in that sense. Yes, so these are the main results, and yes, right. So, but actually we did not solve the problem fully, and we have several limitations in our approach to solve that verification problem. And to name a few, our approach still finds some loose error bounds for some cases. And in some cases, we have to do quite a lot of computation. And yeah, there are a few more, but I'd like to skip due to time limits. And yes, so this is what we did. And to summarize, we attacked the problem of verifying math.h implementations. And we encountered two main challenges in solving the problem. And we partially solved those challenges and obtained some satisfactory results for some benchmarks. And that's it. Thank you for listening.
Really great talk. Thank you, Wonyeol. Let's take one question and I'll just take a question off of actually, I'll just ask my own question here since I get to choose. So I was interested, you mentioned, these special cases where floating point results in less error than you might naively expect, like exact subtraction. And I remember from the paper, there are like 3 or 4 more of these. Is this some like small denumerable set where we could come up with like the 10 special cases that are necessary? Or do you think this is a case where sort of every implementation discovers its own new trick that floating point supports that is necessary for it to work?
Yes, that's a very good question. So in our paper, we only use several like 4 or 5 exactness results. And that was sufficient to prove the one-off error bound. And I think there could be numerous way of doing such exactness computation in the floating point, but I think those exactness results used in practice are quite limited. But I want to point out that they are not very well organized, or I mean, they are not listed in a clean way in a single paper or a book, but they are kind of spread out and known to floating point experts only sometimes. So we had a very hard time to find out those exactness results by hand or some I mean, we was struggling to find out those exactness results. But anyhow, I think only a few of those exactness results are used in practice to implement those libraries.
Okay, thank you. Yeah, really great work. So our next talk is from Deming. So if you want to, oh, great. And if you could start the recording on your end as well.
Yes, I'm trying to find the record button.
Yeah, so in that gray bar that's floating on top of your screen, there's a ... at the right-hand end.
Oh yeah, I see. Okay, start the recording. Good. So let's start. And hi everyone, and thanks for coming. I'm Daming Zhou from Peking University, and today I'm glad to be here to introduce our recent work detecting floating point errors via atomic conditions. So let's start. Before the detailed introduction, I would like to first highlight our result first. Last year, DEMC was proposed for detecting floating point errors, and it cost about 8 hours for analyzing 49 functions from GSL. And our tool on the same benchmark only needs 21 seconds for analyzing them, so which is more than 1,000 times faster, while at the same time, we detect 40% more floating point errors. And this is the outline of this talk. In the first section, I'm going to introduce floating point errors and most existing approaches to do that. And here is an example. We know that there are always floating point errors, and sometimes the error can become significant. And here, like this example function contains only 4 basic operations here. When we try a specific input like 10 to the -7, the result becomes significantly inaccurate. It only contains 3 valid digits. So how do we find this kind of erroneous inputs? Like the existing approaches, most of them treat the floating point program as a black box, and they heavily depend on the Oracle F. Like they first calculate the floating point result, and they also calculate the Oracle result, and to get the error of this input and repeat this procedure to find the erroneous triggering input. And also, since the high precision since the Oracle is only conceptual, most of them use the high precision program to simulate the Oracle. But at the same time, we notice that the high precision program is not a silver bullet. It brings several difficulties that are not solved yet, and which we will discuss in the next section. We find that using high precision types is very expensive for 2 reasons. The first one is they are expensive in computation cost. Even quadruple precision are more than 100 times lower than double precision, and for MPFR, the overhead further increases. And the second one is they're expensive in development cost, because we cannot simply change all variable to high precision types to get a more accurate result due to the existence of precision related operations and precision specific operations. And since the time is limited, I'm not gonna discuss about these 2 kinds of operations, but we know that this kind of operations need to be manually found and handled to get a more accurate result. So it's kind of expensive in development cost. And so it leads to the need for an Oracle-free approach. And we know that if we have the Oracle, we can distinguish this input with their errors. So the question is, how can we analyze the floating point program without Oracle, since we have no idea whether result is accurate or not? And this question leads to our approaches in the next section. In the third section, we're gonna discuss the concept of atomic condition and our analysis based on atomic condition and our approach atom. We start from the component of a floating point program. Like a floating point program can consist of atomic operations, such as basic arithmetic and basic functions, which we define as an atomic operation. And we also know that the error on this atomic operation are guaranteed to be small by some definitive documents. So why does the significant error still exist? We find out this is because the error is not just introduced and propagated through these operations, but also significantly amplified by certain operations. And to understand how these errors are amplified, we adapt the concept of condition numbers here. The condition number is a concept from mathematical analysis and in numerical analysis, and it measures the ratio between the error in the input and the output. In other words, the condition number measures how much the relative error will be amplified from the input to the output. For example, the condition number on cosine x is x times tangent x. And for different value of x, the condition number, also the error amplified factor, will be different. And by focusing on condition number on these atomic operations, we can know that during an execution, which operation may amplify the error and become risky. Here comes out the key insight of this paper. We define the concept of atomic condition as a condition number on atomic operations. By leveraging atomic condition, we can analyze floating point program in a white box manner. and we can measure how much the relative error is amplified by atomic conditions, and we formulate that atomic conditions are the dominant factor for floating point errors. Since atomic condition only needs native floating point types to compute, we can get rid of high precision types, and which will significantly accelerate our analysis. Here we use the example to show the relation between the atomic condition and the floating point errors. This is the example function and also an example program here. We know that at the operation level, for each operation, the error in the input will be amplified by atomic condition, and also add an introduced error that together becomes the error in the operation's output. And for a specific input 10 to the -7, we check this step by step. In the first operation, there is no error in the input. Atomic condition is very small, so there is only a very small introduced error in the output. And in the second one, the input contains a very small error, but the atomic condition here is very large. So the error is amplified significantly by this operation and become a very large error in the output. And in the third one, there's no error in input, condition number is 1. So the output contains a very small introduced error. And in the last one, there is a significant error in the input, and condition number here is 1, which means the error will just pass to the output of this operation, which is also the final result of this program. And how to calculate atomic condition? Like we have the condition, definition of condition numbers here. It involves a derivative of the fx. And since we define the atomic condition as the condition number on these atomic operations, and their derivatives all have mathematical expression, we can use pre-calculated formula to calculate them. Like for cosine x, their atomic condition is x times tangent x, and we don't need any other high precision thing to do that. We can directly calculate it with native floating point types. And by analyzing this formula, we can distinguish these operations into 2 categories. The first one is potential unstable operations, such as addition, cosine, and log. For this kind of operations, their atomic condition can become significantly large if the operand falls into the danger zone. And for the other one is stable operations, such as multiplication and square root, because by analyzing their formula, we find that the atomic condition on these operations are always less than or equals to 1. And all the previous discussion lead to our final approach here, atomic condition guided search. This is a dynamic search-based approach. And in this approach, we first generate input and track its execution and calculate the atomic condition on each operation. Our goal is to find the largest atomic condition on each operation. And as the search continues, we may find some operation involves a very large atomic condition, and it may lead to erroneous intermediate result and may also lead to erroneous final result. And we use an evolution algorithm here to act as a search module, and also the other search module can be easily interrogated. So in the last section, we're going to discuss how effective and how fast is our approach. We conduct our experiments on the GSL, and we find that 42 of 88 functions have significant errors here. Like here is the histogram. We find that some of them on the left hand do not have severe floating point error issue, and on the right hand, there are some of them, like 42 of them, have severe floating point error issue. Also, when compared with the state-of-the-art technique like DEMC last year, our approach finds significant error in 8 more functions, which is 40% improvement, at the same time incurs no false negatives. At the runtime cost, Atom needs only less than ½ second for analyzing one GSL function, which is several orders of speed ups over the state-of-the-art, which also makes our approach much more practical. So finally, some take-home messages. In this paper, we introduce a atom, which is a super fast and effective technique for detecting floating point errors. We also introduce the concept of atomic condition, which we believe is a powerful tool for analyzing floating point programs. And it brings several advantages, such as oracle-free, native, and informative. Because of these advantages, we expect atomic condition to have a broader applications, such as debugging, repair, and synthesis. That's all. Thank you.
Okay, great. Thank you so much, Daming. I think the first question we'll have from Sangeeta.
Hi, Daming, nice talk. Can you find input which can result in high error due to accumulation of the rounding error?
Yes, excuse me? Yeah.
So basically you introduced that you can find input for what I understood is due to cancellation, catastrophic cancellation. But can you also find input due to accumulation of rounding error?
Here, we're trying to find that input that triggers significant atomic operation, like we focus on the locally. And if there is a significant atomic condition, it will lead to an erroneous intermediate variable, and this input we mark it as suspicious. And at the end, there may be some dozens of suspicious input, and we need to validate to check that if this input really triggers a significant error.
So if you have a program and there is no subtraction in that program, can you still find input which can incur higher error?
What do you mean by subtraction of this formula or something? Yeah.
It's okay, we can discuss offline. Thank you.
Yeah. Okay, sorry, thank you.
Okay, let's take one more question from Jackson.
Daming, great talk, man. So I wanted to ask about the set of functions that you used for your evaluation. So you said you pulled 88 functions from GSL, and I was just curious about what was the criteria by which you chose those functions, and was there a common factor or how that worked?
Okay, we chose the GSL function from the spec function folders here, and they are all kind of like Bessel function, gamma function, and some kind of these functions. And this function we chose, they only contains one parameters, but our approach is not limited to that. We just do it as the other papers do, so there's an easier comparison for them. And actually, this is kind of all of them I can find, and there is about 107 functions, and there are 88 of them. We can find an oracle function for them. We need oracle, not the atom need them, but we need oracle to validate our result. So we finally choose these 88 functions from the GSL library.
Great. And what was your oracle that you tested against?
The oracle we use from the MP-math, which is a Python library, and I think basically they are using the MPFR and implement their own these functions, MP-math. Yeah.
Great, thank you.
Thank you.
Okay, and our final talk will actually be Jackson. So we've already done the audio test. And Jackson, if you could make sure to start recording and then go right ahead.
Sure thing.
Okay, so you're recording.
Great. All right. So
if you haven't, you'll want to share your screen too.
Am I not sharing my screen? Oh. Thanks for catching me before it was too late. There we are.
All right, we can see it. Thank you.
Great. So hi, everyone. My name is Jackson Vanover. I'm a graduate student at UC Davis, and I'm here today to talk about our team's work on discovering discrepancies in numerical libraries. And this talk's going to appear at ISTA in July. So apologies, the target audience is more of a general software testing audience, so some of the preliminaries might be a bit obvious, but bear with me. So to start, we'll start with the question, how do we know if a numerical result is correct? And we'll give an example here. Say we are using the NumPy library and we initialize this matrix with those values all being 132 and some change, and we take the mean. And at this point, we sort of have an intuitive idea. We have an intuition about what the result should be. It should be that 132 and some change, that exact value, since all of those are the same. But we see this and we know that there's an error. There's something that's not lining up. But the question is more interesting when we pull out, say, a function like the anger function from the JMAT library. We give it this input, we get this output. We don't know, we have less of an intuition about whether or not this is correct, right? Which brings us to the motivation here, which is the fact that test oracles are hard to find. Now in this domain, right, one of those possible solutions like Daming was talking about is using high precision, and he talked about some of the downsides, so I won't go into those, but it merits asking for an oracle-free approach. And so here we'll offer one potential strategy, which is to identify other functions that implement the same analytical function, give it the same input, and look at the outputs and look for a numerical discrepancy. And in this case, we view one. We can see that JMAT is clearly the outlier, and that sort of points to this anger function implementation not being quite correct, something suspicious. And so really what we're talking about here is differential testing, right? And in this case, then the problem overview, what we're concerned with is implementing such differential testing, but in an automated manner and for numerical libraries. And we've identified 3 challenges in doing so. The first of which is extracting signatures, synthesizing drivers. We want to extract signatures that are the target of our testing within our scope. And we want to synthesize drivers because we have to execute those functions. We want to automatically discover function synonyms, and we define function synonyms to be function synonymity to be an equivalence relation that partitions the set of functions into equivalence classes. And this is non-trivial because documentation can be lacking, function names can be misleading. So it merits another approach besides just manually constructing those classes. And lastly, we want to identify meaningful discrepancies because not all discrepancies are indicative of buggy behavior. And that can be due to the inherent imprecision in floating point numbers, different choices with regards to implementation with like branch cuts and function polls or error handling. So we need to have a mean of triaging discrepancies. And so here we see our solution to this problem. This is FPDiff. It is an end-to-end tool for automated differential testing of numerical libraries, and it takes in the source code for the libraries that are being tested, puts it through these 3 components here that we see depicted, and ultimately generates a set of discrepancies. And these 3 components that you see here actually address those 3 challenges that were outlined on the previous slide. Today's talk is actually just going to focus on challenge 2 and 3. Challenge 1 is dealt with in our paper, which there will be a link to at the end. So challenge 2, which is finding function synonyms, this function classifier will conduct multiple evaluations over a series of elementary inputs that it also takes as input. And we define these elementary inputs to be inputs for which we expect these functions to exhibit well-defined behavior and ultimately generate a characteristic vector from these multiple evaluations. So to give an example, here we have a set of elementary inputs, and for our experiments, we generated those randomly and uniformly between 0 and 3. We've got drivers in the left column. We have all our characteristic vectors in the right column. And as we evaluate all of these drivers over each of the elementary inputs, we populate our characteristic vectors. And then ultimately, function synonyms are going to be the drivers corresponding to the functions that have the same characteristic vectors. And here we see highlighted in yellow a subset of the equivalence class that was used in the example previously, representing regular cylindrical Bessel functions. So these equivalence classes are then given to the differential tester. The differential tester takes also as input adversarial inputs, which are intended to provoke divergence between those function synonyms that we've discovered. These can come from a bunch of different sources. For our experiments, we used test migration inputs from each of the libraries. We used inaccuracy-inducing inputs found by a modified version of the S3 FP tool, and we use special value inputs like nan and infinity. But you can use whatever you want. It'd be interesting actually to use some of the inputs found by like Daming's tool, for instance, to see what sort of discrepancies we can find. But here's an example using that equivalence class of regular cylindrical Bessel functions and that input, which was a test migration input from GSL. We see that discrepancy that we saw before, and the differential tester will identify it as such. And we'll assign it a category. And this categorization, we provide 6 categories based on characteristics we observed in the discrepancies. And this is one of our contributions in the paper. I don't have time to go through all of them now, but suffice to say that they're organized higher numbers being corresponding with more severe discrepancies that are more likely to indicate buggy behavior. And in this case, this is a category 3 discrepancy, which is an inaccuracy. So our evaluation, let's talk about the function classifier and how well it finds function synonyms. It generated 310 mappings between function synonyms with a 95.8% precision and a 79% recall. Ultimately, this resulted in 126 distinct equivalence classes of special functions that represented almost 500 of those special functions across GSL written in C, JMAT written in JavaScript, and MPMath and SciPy written in Python. We calculated the precision and recall manually. And the precision was affected by the choice of elementary inputs. So there were about 4% of them, the mappings that were discovered would diverge for negative inputs, which were not used as elementary inputs. And the recall was mostly affected by the capture rate of the extractor component that came before the classifier, which is to say that a more complete set of drivers given to the classifier would generate a more complete collection of mappings. And then we have our differential testing component, and we want to know how well it found these discrepancies and if it could figure out which ones were meaningful. We generated 655 unique discrepancies, and these were reduced by about half to 327 based on the assigned discrepancy category, and these we inspected manually. We found 150 of those to represent reportably buggy behavior. And in particular, those 150 discrepancies represented 125 unique bugs. We reported all of these to the library developers, and to date, we've seen 30 fixes, 9 were found to be previously known, and 25 were acknowledged, but no fixes yet. So I just want to conclude then with just 3 examples of discrepancies that FPDiff found. This first one is a category 1 discrepancy, which were the discrepancies that were dropped from the complete set of 655. Category 1 discrepancies are not reliably very buggy. They're not as severe, and they sort of represent these cases where library developers made different choices with respect to the implementation. So here we see a test migration input from SciPy, and as a result, GSL and SciPy show that they're not supporting this particular portion of the domain, and the NaN and the domain error are documented in the documentation. But JMAT and MPMath do support it, and they return a complex number. So not a bug, but illustrative of different choices made by library developers. The second one is a category 4 discrepancy for an equivalence class of Hurwitz zeta function, and this is a special value input that prompted this, an infinity in particular. And we see that these libraries don't agree on the asymptotic behavior of this function. Combine that with the fact that JMAT supports limit evaluation elsewhere in the library for its special functions. This resulted in a report being filed, and we were able to suggest the proper behavior just by looking at the consensus in this equivalence class. And then the last one I want to talk about here is an inaccuracy-inducing input caused the discrepancy here in the equivalence class of the polygamma function. This is a category 2 discrepancy, and here we see that this input, which was generated by S3FP, maximized the error between those first 2 function synonyms there, the GSL and the MPMath one, and we can see that in the outputs there that discrepancy. But what was more interesting was the fact that when we applied this input to the rest of the equivalence class, we observed further that there was a discrepancy between MPMath's 2 implementations, one of which returned a complex number. So this single discrepancy resulted in 2 reports. So in conclusion, to wrap it up, here we've proposed an approach to discovering numerical bugs that's Oracle-free. It's implemented as the tool FPDiff. And it utilizes function evaluations over elementary inputs, which we found to be an effective means of discovering function synonyms. And in the paper, we proposed a categorization of numerical discrepancies. The takeaway from this talk is that some categories of numerical discrepancies are more likely to be severe than others. And ultimately, we found 125 unique bugs. And that's my talk. Thank you very much.
Thank you, Jackson. Really cool work. So we've already got some questions queuing up. So I guess, Zach, do you want to go first?
Yeah, so we've thought about doing some of this, or something a little bit similar in FP Bench. One of the things I really like here is that you're looking at like code from the wild, which is really cool. One thing that we've struggled with is that a lot of times the different libims used by different languages just have subtle differences at the lowest level, right? So like when we compile an FP core with Go versus JavaScript, we get different behavior just because sign has different rounding error. But everything else is sort of okay. So I was wondering if, can you tease apart that kind of error? And then maybe well, actually, let's start with that question.
Yeah, so that's an interesting question. If I understand you correctly, we're sort of asking about figuring out the cause of some of these errors, and if there are a particular like group of causes of these errors that our tool is able to detect. And we didn't go too far into actually parsing all of the bugs themselves and figuring out what was the cause of the errors. So it may have had to do with those underlying libm implementations, but I'm not sure. So that'd be interesting work to follow up on, look at some of the reports that we filed.
Yeah, maybe one thing that wouldn't be too hard, I'm not sure about this, right? Just total brainstorming. Yeah, I suspect there is a fair amount of code sharing between some of these. Like the underlying libm for the OS is probably usually used. And so some of these codes are taking the same path, but clearly a lot of them aren't because you found a ton of bugs. So it'd be interesting also to kind of maybe try to figure out, like, can you avoid generating tests when you just see that all these different implementations are taking the same code path through the same system libraries? So they're going to do the same thing. You can avoid time generating random tests. And then in situations where they're actually touching different shared libraries, then there's at least a chance of them doing something different. Some ideas, but really cool work.
Thank you. Yeah, I think that's a really cool, one of the things I like about this framework is that I think there are a lot of different things that you could plug into it to like further your insights into what's happening behind the scenes, and some sort of like trace through the programs to figure out what actually is being called under the hood would be really illustrative, I think, and would be really informative. So yeah, I like that idea a lot.
Okay, cool. Thank you again, Jackson. I think it's been really great to see all of these talks, and I'm going to take just a moment now to close out FP Talks 2020. So if you'll just give me one more minute of your time. So I wanted to basically say thank you, everyone, for showing up. It's been really great. I've had a blast watching all of the great talks today. I've learned a lot, and there's a lot of you that I want to get back in touch with for further details and more collaborations. I'd also like to say thank you for everyone who participated. You're showing up, listening, and hopefully sort of engaging more with our community is exactly the goal behind us putting on FP Talks. I just want to say a few words before we wrap this up. First of all, I'd like to thank the Applications Driving Architecture Center, and of course, the fact that so many of you have been involved with FP Bench in one way or another over the years, and that's sort of the project that we're putting together, FP Talks, under the umbrella of. I also want to say that this is not, though this is the end of FP Talks, this does not have to be the end of sort of the small community that we've gathered here and the topics that we've discussed. First of all, as I mentioned, we've got a bunch of resources that we've developed under the FP Bench umbrella, and those are the benchmarks, the compilers, the standards. Any way that you want to make use of those, contribute new benchmarks, or participate in the standards, that'd be fantastic. The other thing that we want to do in FP Bench is form some kind of community. I mentioned that one of our efforts was these FP Talks, but that was actually also a Trojan horse for a second effort, which is that you're all now on the FP Bench Slack, and don't need to do anything to continue being on it, which will just be a place where we can continue discussing these questions, go deeper in discussion on some of the talks we've seen, and also talk about ways that our community could collaborate better together. So in summary, thank you everyone who's participated. It's really great to have this all come together. And with that, that's the end of FP Talks 2020. I guess see you in a few minutes in the gather for any final drinks and discussions. And also, I think everyone should take a moment to thank Pavel. It was a huge amount of work
to put the event together. Really, really great leadership, Pavel. This was a spectacular event, especially considering everything going on. So major kudos to you pulling this off.
Thank you all. All right, I'll see you all in the gather shortly. We'll do the after conference drinks, and you can pretend to be catching an airplane if you need to go.
Thank you, Pavel.